Welcome to my new calculus channel. My name is John Gabriel, and today I'm going to be discussing epsilonics, which is one of my favorite topics, simply because it gives me a chance to shame the big stupid or mainstream academia and to show exactly how ignorant, incompetent, arrogant they've been throughout the past few decades. And the fact that they do not listen to reason because academics hate to be shamed. That is probably the worst thing that you could do to an academic, is to show him that he is wrong. And they never like to admit they're wrong. And very few ever admit they're wrong. Okay, so in this video, I'm going to talk about epsilonics and the flawed calculus. So let me close this window here, and I'll start now with an explanation. So you've probably seen this expression millions of times, okay? Limit as h goes to 0 of this finite difference quotient, like so. This is a piece of crap that was invented by a series of French mathematicians. We begin, first of all, with Cauchy, and we have a lot of influence from Weierstrass. I don't think Weierstrass was French, Weierstrass, and several others. But at any rate, these orangutans try to rigorize calculus. And this here has never rigorized calculus, because if you look at all the other videos I produced, you'll see that f dash of x is actually a function of the difference quotient, the multivariable difference quotient, when h is 0. And that is equal to f of x plus h minus f of x over h. Okay, so now you'll see immediately that this here is actually impossible, because h cannot be 0. And if you have any particular curve like that, and the x-axis here and the y-axis, and you're trying to find the slope of the tangent line there, these secant lines which get closer can never have the same gradient as a tangent line. And so this rot is based on this original Newtonian boo-boo, okay, or Leibnizian boo-boo. Neither Leibniz nor Newton nor any other idiotic baboon that came before me understood calculus. And they were trying to rigorize it. They failed. Cauchy failed, Weierstrass failed, they all failed. And I'm going to show you now what they tried to do to pull the wool over your eyes, okay? So essentially what this here gives you is, it gives you the derivative plus some expression in q and h. This has to be 0, okay? If this is not 0, then you don't get the derivative, because it's the sum of these two which must give you the derivative. Now, in my resilient new calculus, it's provable that q, x, m, n is always equal to 0, all right? So you can study my new calculus and find out those things for yourself. But so what did the monkeys try to do to rigorize their bogus calculus? Well, it started off with Cauchy beginning to come up with these particular ideas. So Cauchy was looking at a certain area and saying that if these distances from the point of tangency get smaller, then so do the distances from the limit. And now, one of the things you need to notice here, by the way, is that you have to have an inverse for the particular section you're looking at, even if the function doesn't have an inverse on that section. you understand? So what you're basically looking at here is a region in which the particular definition is true. So in other words, you guess using, you first of all work out your guess according to this function here, because that's all you can really do. You don't have in your bogus calculus a rigorous method for finding the derivative. You just can't. What you have to do is you first have to guess it using this, then do some bogus arithmetic here by setting h to 0, and then you take whatever you find as a derivative and you go back here and you check to see if that is actually the derivative or not. So it's a very long, tedious process, which is bullshit, by the way, because it doesn't rigorize calculus. It just states a very obvious fact about a limit, okay? And this statement here is a very obvious statement about the limit. It doesn't define the limit. It verifies the limit, okay? Very big difference between defining and verifying. And of course, the limit may not be the same as a derivative. But that aside, there are many problems with the standard definition, because in this definition here, in fact, in this particular definition, let's just go back here. Oops. You have to know L, which is a derivative. So you can't use this to find the derivative, you stupid fool. You get that? You need L, right? Otherwise, you can't find the derivative. So you use a little botched up method to get your derivative, set h to 0, which is, you know, what a monkey would do. And then you test it using this definition. Okay, so I've taught AP Calculus, and I've had to teach all these concepts. And when I teach these concepts, my students understand, right? So I often have to come up with ingenious methods to get them to understand. And one of the methods I came up with was the inverse method, the inverse function method, which I demonstrate in this particular article. And this is a link on the top here, and you can go to it. And what this does is it shows you how you can use the inverse method. You don't have to use any inequalities. There are no inequalities whatsoever, because inequalities are very error prone. You can make a mistake without even trying. You can make a mistake, okay? So this here shows you how to find those regions without any inequalities whatsoever. And the nice thing about this method is that it can be used with any particular function that has a limit. And I've shown you various examples. Yeah, I've shown you the square, this quadratic, and I've shown you, let's go on here. I've shown you square roots. Where is that? Let's go down here. I've shown you more quadratics. I've shown you, and then I've also shown you how it works using the mainstream approach, how you would solve it. And then I give you several other possibilities like sine x and the like. And so you can see how to apply this method with any function that you get. Now remember, the region that you're looking at must have the limit in this particular shaded area, and you must be able to map the x value onto the limit. You'll also hear something else in mainstream mathematics which says you may have a limit, but the function is not defined there. Absolute bullshit. If there is a limit there, then the function is defined, okay? And you cannot remove this point from a function by multiplying it by a certain ratio which is equal to 1. You just can't do it. That's nonsense. That's monkey business. All right, so this particular method that mainstream academics use doesn't prove anything. It doesn't even rigorize calculus. All it does is build up using the crap of first order logic and set theory, a whole trash heap, a pile so large that you can spend the rest of your life learning the stuff and still not get it right and still not understand. And I'm telling you this because I've spoken to many professors who don't know what they're talking about. And always I confound them, all right? always I show them that they're wrong. So this finite difference, if we had to change this function here and make it, let's see, quadratic, the same thing happens, okay? So you'll still see, whatever you do here, that there's a limiting region, and we can just bring these down a little bit. Come on, I want to move these. Moving graphics view, so let's do this. There we go. Right, so again, the same thing happens here, okay? It doesn't even necessarily have to have an inverse, because, I mean, if you look at the square root function, if you look at this function here, it doesn't have an inverse everywhere, does it? Let's see. Okay. Come on. It's a little slow right now, because I'm actually recording. It's always slow when I record. Okay, so this is, oops, this looks kind of funny here. Well, that's because I've got some things on here. So yeah, let's remove the monkey business one. Okay, so the monkey business is just the finite difference quotient of this square root function. But at any rate, we can see what happens as we increase this region. Come on. Oops, should increase. No, I don't want to do that. Seems like I'm not able to use this pen device properly. Well, that's just too bad. Let me see here. Well, so if I go along there like so, oh, I'm sorry, I have to, the way to increase it is as follows. I'm doing the wrong thing there. Right, there you go. There you go, there you go. Okay, and now we can move that one closer too, and we can see what happens as you change the regions. So as you change the points where you're calculating the finite difference quotient, okay, you'll always see that it will fall into this region here if it complies with the epsilonic statement that verifies it. So if you have a truth table like this, if it goes outside of this region, it'll be false, okay? And anywhere inside will be true, anywhere outside the region, it will be false. But we could always extend that region, right? Let's extend that region somehow, like so. And if it's false right now, but if we do this, it should be true, see? Okay, so at any rate, because I felt sorry for mainstream academics, shared with them another theorem that I came up with, which is the geometric limit, which you only need to prove once and it works for every function. What it basically says is this, that if epsilon is greater than that distance and delta is greater than that distance, then the area of the circle given by this expression reduces to 0 as x approaches c. And it will work for any function. So if I approach this, can you see this circle here? The area reduces to 0. And when I get to that point, it is 0, okay? So, and it can be any function. I mean, that's a square root function. If we have, let's bring this reasonably close because I don't want to adjust my graph. So the further away you move, the bigger the area gets, okay? Now let's just get close by here and let's change the function again. It doesn't matter what function you put inside here. This theorem works for all functions. And I advise you to study it. There is also a document on it. I've actually covered this in past videos. But all right, let's see what happens as we move this away. Do you see the area gets larger? And as we move it closer to the limit, the area of the circle gets smaller. And you can test this with any function. This limit theorem works regardless of what function you have. So you only have to prove it once and you never have to worry again with this bullshit down here. Do you see this? You don't have to do proofs like this. You don't have to write up a minimum of delta and epsilon, which is a total waste of time. And you don't even have to use my ingenious inverse method, which I've shown you in this particular file here, okay? So all that nonsense falls away, and calculus doesn't require any of this. This here doesn't rigorize calculus. It just adds a lot of trash onto the big trash heap that is known as mainstream calculus. Makes it harder for you to learn, and you get to a point where you really don't understand anything anymore. You're just memorizing like the idiots on Sci.math or Math Stack Exchange or XKCD or any one of those other trashy sites, all right? So what I've tried to do here is just show you that you can actually use the inverse method, or alternatively prove my general method of the new limit theorem, okay? The new limit theorem states this: once you prove this, you don't have to do anything again for any function, because the limit will exist if this area reduces to 0, and it can be shown. I've also proved this, and there's a proof of this on my Google Drive, okay? So if you come here, I've got articles, and you can look through here and you'll find that proof. So I hope you've enjoyed this, and I don't think there's anything else I need to add right now. I hope you'll join me again next time for another exciting episode or video where I expose mainstream stupidity, and you'll learn a lot more from me than you learned in all your school years and in all your career of mathematics. I am the great John Gabriel, the discoverer of the first and only rigorous calculus in human history. More advanced alien civilizations may already know of it. Till next time, goodbye.